Hello again. Welcome back to Information Storage and Retrieval. Last time we talked about various ways, not various, only a couple of ways to implement how you can actually traverse your dictionary when you are searching for a term inside it, right? The goal being we're going to pull out the postings, right? We want to go into our index and find the postings in every way that we use these things. And to do that, we have to know what the structure is going to be in our system. So the two structures we talked about were search trees, which are nice. They have this constantly logarithmic runtime. They have a logarithmic runtime. And they will always have a logarithmic runtime, which is great, regardless of the size. And they can enable some tricks for free, which we'll talk about today. And then also hash tables, which are thankfully very intuitive with how we actually use them. You'll see them soon in the assignments. And they have this near constant runtime, at least at small sizes of dictionaries. You end up with a little bit more collisions, hash table collisions, if you have a very, very large dictionary. So that can lead to slightly less than constant access time. But, so today we're going to talk about tolerant input. It's this idea of allowing the user to input things that aren't exactly a specific search query. So that's where we'll start. So far, all of our queries are very rigid. The way that we have to specify them, the way that we process them, the terms have to be precise. Now, there is some wiggle room there because we've talked about equivalence classes and how you might have a baked-in one like window and Windows collapse together. So they don't have to be perfectly precise, but they still have to be kind of conceptually precise. And the issues with these kinds of queries, this like sort of rigidity of our queries so far, is that there's a couple. Functionally, users might want to specify more than one kind of, not kind, I suppose, but they might want to under-specify their term, right? They might want to partially match a term. Say they only know one piece of a word, but they know that that piece is at the beginning of the word. They might want to search for any terms wherein that piece of the word is at the beginning, right? Another element here is errors. Humans are noisy. We make errors. Our systems interfere with us sometimes and help us make errors, like in autocorrect. There's a lot of ways to make typos, to make small errors that, to be frank, if your system does not handle them, it's going to be really annoying, right? We need systems that can be a little bit tolerant of these very minor issues in the way that we input the text in order to help us just get the user on with their day, right? So if you make an error when you're inputting, you want your system to have tolerant input. So tolerant input covers both of these bases. The idea is it's a set of processes, it's a variety of things we can do to help mitigate errors and increase flexibility when we are processing our searches. So some methods we're going to look at are wildcards, spelling correction, and phonetic correction. Today it's almost entirely wildcards. We'll just have some lip service to the other two, which we'll cover next time. So let's talk about wildcards. This is our first step into tolerant input, and it's great. It lets the user do more than just the strict term matching. They can engage in partial matching. So they can specify just a few letters and let the system then say, okay, I'll go get every term that matches those letters, and then we'll do the search based on all of those terms, right? So the query CA star being the wildcard character in most cases, returns anything that starts with CA. car, cat, call, camp, all that. So here's an example here. Another way we can use them. So let's say we have in our mind something we're looking for, some term we're looking for, but we can't remember everything about it. So we know that it starts with the letter C, and we know that it ends with the letter T. And we're not sure what's in the middle. This is where we can use the wildcard query, right? So the way we would construct this as a user would be C asterisk T, meaning, hey, I know the beginning is C, something happens in the middle, and then T is at the end. What this will go through our dictionary and do for us, this wildcard query gets expanded, query expansion, into a set of terms. Cat, that satisfies. Can't, that satisfies. Cart, couldn't, caught, and so on. Now, this is not a very useful query, it's just for illustrating how this works. When would I need to know about cats or can't or cart or couldn't? But the idea is that this allows you to say, hey, there's a piece of this term, there's a piece of this concept that I've lost. You know, a lot of times we can remember the first part of a word, but maybe not the end of it, right? So we can specify that. And what happens is, this turns a normal singular query into an expanded query that instead of, as we've done before, we typically find the intersection of all the postings, right? Well, this time we'll find the union. We'll say, okay, for this specific term, I'm going to blow it up into all these other terms, and I'm going to OR all of them. I'm going to go get all the postings for any of them and then process them. So this single term, one little piece of our perhaps more complex query, can be blown up into a set that we will then take the union of every possible item for. So, wildcards. This gives us the ability to expand a search to enable partial matching. Now, how do we do wildcards? We're going to talk about a few different ways. First, a couple ways using trees, but that's more for conceptually understanding how a lot of these systems have worked and can work. Then we'll talk about k-gram indexing, which is a little bit more our speed and how we'll tackle some of this stuff. So back to trees, right? We've talked about trees. If we're using trees to search our dictionary in our index, we get a little bit of wildcard functionality for free. We can do trailing wildcards very easily, and I'll show you how. The basic idea being that we can just stop traversing the tree and go get everything from it. If we want to do leading wildcards, we'd have to do a little bit extra. So let's talk about how do we make this work using trees. So wildcard traversal. The basic idea is, like we would do with an actual fully specified term, we'll walk down the tree, right? But we'll stop when we get to the wildcard symbol in our query, in our wildcard query, and then we'll just grab everything. So, and again, we will then expand the query to include all of these options, all of these possible terms, sets of postings instead of just one. So how do we do that? Let's look at another tree traversal as we've done before. So this query, this wildcard query, is T asterisk. That means, hey, give me any term in the whole set, in the whole dictionary. I want any documents with any terms that start with T. So how do we do that? We'll traverse down, we'll start with T. Well, remember, when we're using the dictionary structure of a tree, we'll then say, okay, so it's down here, L through Y. That's where it starts, okay? Now, it's not through I to S, it's definitely through T to Y. We have all the T's are here. Great. So we've reached the end of our ability to discern anything. As we would normally do, we'll just go to the next letter. Oh, the next letter is the asterisk. I'm going to get everything under this node. Whether that's, just them and there, or if it was a larger dictionary, we would stop here and just get everything that starts with T right here. Cool. So that's a trailing wildcard. That's nice. We're able to do this for free. We did our whole... Because of the way that our dictionary works by default, we can just go ahead and process those kinds of queries straight away. This requires no extra effort, and it's pretty nice, actually. A lot of searches are really only going to care about leading... So a lot of wildcard searches that users do are really only going to care about those first few letters. Those are the things that we remember anyway, right? The beginnings of words. So if you're happy to just have, if you have a huge database, collection, unstructured collection, and you're choosing to implement trees because of that, you get wildcard leading or trailing wildcards for free. That's pretty cool. But to do leading wildcards, we need some other tricks. So we need to be able to do this same process, but in reverse. That sucks for trees, because trees are built, at least the way that we're using them here, they're built based on the first letter, the second letter, the third letter. We can't really redo the structure. So instead, we can build a reverse tree. This is a tree that it's the same thing, but we have constructed it with the terms all flipped backwards, wouldn't you know? So look at this backward dictionary, right? And how are we going to build this tree? The exact same way. So D to ma, M-A to M-A-I to U. So it's the same basic idea, right? We are putting in these cutoffs for where the different letters go. Now, you might notice this looks a little bit messier because a lot of these words end with the same letters. So there's a whole lot more that fit under each binary slice. So to really let's go back a little. Oh, okay. Half of the letters are from, so half of the terms, right, are from D, so dlu, so wood backwards, up through ham, right? Ham in reverse is ma. Well, but MA is also in Sam-I-Am, except in reverse, right? MA. So to differentiate these two, to make our first cutoff, we have to go all the way through ma and MA-I. Okay. So you see how this is just a property of this particular dictionary, but just so that it's clear what these terms all mean. So now if we're going to split these up further, so let's look at the top half first. Wood backwards still starts with D, still that's fine for differentiating. We have another split. So what does this first set contain, right? It contains ham, ham, I, anywhere, there, here, like, and wood. Right? I'm going in reverse order here. So just looking at the top set, again, we got to split it in half. We have here and there are the splits. Okay, so that's why there's so many letters here required to differentiate each of these sets. This is not super important. I just realized that this looks especially messy compared to the last trees we've been looking at. So the idea being, at each break, we're able to say, okay, I need to run through the word until I find this set of letters that will help me make a decision about which branch of the tree to take. So, but you can see how if we were to process a wildcard in this way, well, hey, we get to process a wildcard from the end of the word. Great. So that allows us to do leading wildcards. So we know how the word ends, and we're going to search down a tree to find all the words that end in those letters. Same way as we did for knowing how the word begins. Now that we have both of these available, we can do both. right? We can combine these and say, I can now know how the word begins and how the word ends and combine the results. So we would search the normal tree for the letters before the wildcard. We'd search the reverse tree for all the letters after the wildcard. And then we intersect those because it needs to do both start with this one and end with this one, right? So let's look at this. We're looking for TH something RE. Now that's a silly thing. You can know immediately what we're going to find as a human being, but the question is, how do we make this system do that? So, okay, we'll look through the left side, the forward side, for TH. Okay, go. Them and their. All right, that's a good start. But now we need all the words that end in RE. Okay, so we reverse that, ER. Okay, so now we have all the words that end in RE, or in the reverse ER, they begin. So here, there, and anywhere. Now we intersect them. Ta-da! There both begins with TH and ends with RE. Cool. So that gets us through the basics of traversal-based wildcards. So we can get both leading wildcards and trailing wildcards out of our processing if we index our documents with both normal and reverse trees, or rather, build search trees to our dictionary for our normal documents, for our normal dictionaries. But that's a lot of indexing twice, rebuilding a second set of trees for this one singular feature. We're going to need a reverse tree dictionary lookup system for much else, right? So we can get a little more clever by building a different kind of index, a permuterm term index. Wait a second. A term index? Not document index. Exactly. This introduces the idea of secondary indexes. As I've mentioned a few times, indexing is this really flexible process that can take basically any set of text as the input, and it will give you an index, right? So all that matters is how are you breaking this thing up into, quote, terms, right? Into the dictionary. In normal circumstances, we break documents down into their terms so that we can search for documents based on terms. We can also break terms down into smaller lexical features to enable searching for terms, to then enable us to search the documents. So wildcards, or all term expansion processes, are themselves a kind of search. So anytime we are trying to expand our queries, we're saying, okay, take this term and go find other terms. That sounds familiar, doesn't it? That's exactly what we've been doing so far, just be using terms to find documents. So this is their own kind of search, and we're trying to find terms. In normal search, we are using the term to go and look up a set of documents. In wildcard search, we're using term features to go and look up a set of terms. Let's double back and walk through this. So, recall, our basic indexing process will take a document collection, represented here, and let's look at the documents. Document 1, cab ABBA. All right. Document 2, babacab. Document 3, abacab. Document 4, baba. Okay. So if we're going to index this, we see a handful of terms. I've used there's only 3 different terms here. To build our primary index, as we've looked at before, what do? Well, we go and pull out the terms into our dictionary for this index. Our dictionary is composed of terms. And we're going to get the postings to the documents, right? So term 1 is ABBA. Where does that live? That lives in document 1 and document 3. Those are our postings, right? Term 2, baba, whatever, that's living in document 2, it's living in document 4, right? Cab lives in document 1, 2, and 3. Okay. We just walked through and built our basic term document index, right? That's our primary index we've talked about since the dawn of this class, right? Now we can build a secondary index, a feature term index. Now feature, I won't use that word very often. This is just to illustrate. We'll always use what the feature actually is. But we can now build an index based on the terms and figure out what features are present in those terms. For example, AB, well, AB, this adjacent letter pair, that's present in ABBA, BABA, and CAB. That's in all 3 of those. BA, that's in ABBA, BABA, but not CAB, right? CA, that's just in CAB. So we've found this is a secondary index. It's an index to help us interface with our main index. A secondary index that our queries can go through to say, oh, I'm looking for several terms. Help me find those first. And then we'll go through the primary index and do the normal, hey, go get me the documents type stuff. So this depends on defining how lexical features, like what are we going to use to actually search for these terms, right? So there's a lot of ways to do this. We'll talk about a couple. To start, we'll just look at permuterms. This is the set of all permutations of a given term, and we'll rotate the starting letter around. It might quickly make sense why we would want to do this. So we use something called a boundary symbol when we're doing this kinds of processing. It's a useful idea. I like to talk about it first, just to get it implanted a little bit better. So to use lexical features, we're going to be breaking the words up into little pieces. It's pretty useful and often completely necessary to have a way to track at least the start or end of a word as well as the letters, right? So internally, we can use this we can represent this kind of any way we want. Visually, we typically use the $, but internally we can also use anything that's not going to be present in most text, right? So when we actually store the symbol, the term, store it to be able to process it into these little tiny lexical chunked features, we track it using a $. So the dictionary term might be capybara, but we might represent it as $ capybara or $capybara when we process it. So just keep that in mind. The symbols that you see are going to represent the beginnings and ends of words. Okay, so let's talk about how we can do all this using this secondary permuterm index. So the idea is we're going to store different permutations of every term in the secondary index. So hello $, will point to hello, but so will LO $H, and so will low $he. All the different rotations. You can kind of think of it as like we're rotating a barrel with hello written on it, and we get to see the front letters every time. So, well, that would be a little strange. We are barrel shifting this, if you've ever seen that word. So what this allows us to do is we can start our search from anywhere in the term. That might seem pretty useful with a tree. The unfortunate thing about trees is that it was really hard. We always had to start at the start. In fact, we had to build a whole different tree to reverse that process. This allows us to start anywhere in the tree and properly find our way to the destination. So if you index your terms using all of their possible permutations, we can then process the wildcards by rotating the wildcard query so that the wildcard symbol, the asterisk, is at the end. And then we do the search as normal. We traverse the tree as normal. So let's look at this. Permuterm index would contain such. Dog is one of the terms that we're looking for. In our permuterm index, all of the following are going to point to dog. Dog $, og $D, G $do, or do. It's weird when you're breaking them up into little chunks, right? But let's say also drug is in the permuterm index. And these permuterms will all point to drug. Drug $, rug $D, ug $der, and G $drew. Okay, so remember that this is a little bit simplified visuals. Just remember that this is a secondary index. All of these left side terms, the dictionary on the left, the postings would all point individually to dog and individually to drug. Just for visual sake, it's more clean here. So now we can process a query. Now remember, under the hood, we're still thinking in terms of trees. We're traversing trees. So I want something that starts with D and ends with G. We already know the answer is that both of these terms do that, but let's show how we get there with this query expansion. So query is D * G. Okay, so what are the steps again? Well, we're going to rotate this until the wildcard is at the end. Because if you remember, with basic trees, we're allowed to stop once we reach the end once we reach that wildcard symbol. So first we need to add the end symbol. So $, right? That's how these permuterms are constructed. So we got to get them into the same shape, right? And we're going to rotate. We're going to shift all these letters right. So $D now, and we're going to shift them right again. G $D, and then wildcard. This allows us to interface in the same way that we would with the trees. So we're going to progress through the letters. And remember, we're looking for the permuterms now. The permuterms are what's at the end of these trees. And we're going to go through the letters one at a time. So G, that matches somewhere. $, the end of the word, matches somewhere. Oh, and now we get the first letter too. D, that matches somewhere in this set. So now both dog and drug have something that matches them. That's excellent. So now our expanded query is D * G becomes dog or drug because they both fit the criteria of that wildcard. So this is useful. It makes more elegant use of trees, and it's adding this secondary index. Powerful idea. So permuterm indexes, they let us skip that sort of reverse the tree thing, and keep with the normal forward searching properties of traversing trees. It keeps it quite nice and clean, at least in terms of tree world. But the issue with these is that they can add a lot of extra storage, right? So for every single term, we have to track every single permutation of that term in the secondary index. And so the longer the word, the more permutations, the more things we're storing just to do all this. So we can work with a less costly and more familiar alternative. But first, let's recap wildcards with trees. When our dictionaries are in trees. So if we're using trees to build our dictionaries, we can do trailing wildcards, leading wildcards, and both at once. Now, initially, we would have needed to create an index with reverse terms, but we can instead build the secondary index to skip all that and be able to search for terms using permuterms. So we've enabled wildcards in a tree-based world. Now, again, trees are used in some capacities. They're actually very important because they are flexible and they always maintain that nice runtime. So you don't have to worry about the collisions of hash tables. But it also means a lot of screwing around with trees and figuring out how to rebalance them and restructure them. A lot of data structures, algorithms, knowledge, right? So we're not focusing on tree-based dictionary development, index building, that kind of stuff. It's very good to know how these trees work and that they are used in lots of places. But that's not how we're going to work with them. We're going to work with the things that we've talked about before as being quite fast, at least for small collections, and really intuitive to work with, and that is tables, hash tables. So, cool stuff if we're using trees, but we are definitely more interested in the sort of the intuitive and runtime benefits of hash tables. Now remember, hash tables are these very fast, lightweight systems of looking things up directly by a string, a name, a term, that kind of thing. So how do we get wildcard functionality here? The answer is that we've already touched on how we can do that with kgram term indexes. Kgrams, our old friends, we can break up any string into the subcomponents of multi-letter chunks. We can do that to terms now. So, kgram term indexes. We've already used kgrams for raw strings and documents before to say, hey, is this order of letters present, that kind of stuff, right? But now we can use it to build a secondary index to search for terms. So the kgram index, the basic unit is going to be kgrams, and the documents, quote, the postings will point to terms from the primary index. So how do we do this? How do we make use of this in kgram world? Well, we can include the dollar symbols as before, and we can use them to track both the start and end of a particular term. So if we were going to break castle up into kgrams, 3 grams, we would have $castle dollar, and we would have all of these here. So $CA, CAS, AST, STL, TLE, LE dollar. The key things here that you should notice are $CA is unique. We're not doing the beginning and ending here. We're saying there's only one chunk of letters that begins this word, and only one chunk of letters that ends this word, and we're tracking that carefully. Now, you can still get some weird order problems in the middle of the words, but again, we are building something that is useful given our infrastructure. So a reminder, so if we were looking for all the terms that have ETR, well, that's going to have beetroot, it'll have metric, it'll have petrify, it'll have retrieval, all that. So that little chunk will be present in all those words. Let's look at how to walk through this. So, our terms, once again, dog and drug, right? Same example. But we're going to look at how this bigram term index is constructed in a similar way. So, for each bigram, remember that each of these terms is going to get padded with a $sign for the start and a $sign for the end. This is key. This is how we keep track of these beginning and end characters, which are super important when we're doing wildcards. So let's do each word, each term. So the bigrams of dog are $D to start. That'll point to dog. Do, that'll point to dog. Og, that'll point to dog. And that's it. So let's do drug. $D is in drug for sure. DR is in drug. RU is in drug. UG is in drug. And $G is in drug. Hey, that's pretty good. So you see how this is very similar to the document indexes, right? The indexes that point to where the documents live. These are bigrams that point to where the terms live. So let's process a query. Starts with D, ends with G. The query is, as before, the user will input D asterisk G. So something, D, something happens, G. That's all I know about my term. So let's break it up into its bigrams, query bigrams. And again, we have to pad it with the start and end symbol, right? So the $signs. So we know that it's going to start with D, and we know it's going to end with G. Well, bigrams are nice because we can just ignore the wildcard part because that symbol is not going to be part of the actual search, right? So we get $D is the first term quote term, the first bigram we will use to look up what the terms are. And it also has to end in G, right? So this is, the stage is set. We have $D and G $. So anything that has the beginning letter is D and the end letter is G, well, which ones are those? D $ will pull out, quote, the postings, dog and drug, and we want anything that ends in G. Pull out the postings, dog and drug again. Thankfully, this time, they both count, so when we intersect this list, we say dog, dog, drug, drug. Great. We have expanded our query in exactly the same way using k-grams instead of the permuterm sort of walking through a tree system. This is great. This is a way that we can keep using hash tables to fully process all of our terms, including this wildcard process. There are some issues when you use k-grams, and this is an issue with any time you use k-grams. But it's nice because there's so few letters, right? But the basic process can still screw up. So if I say DO $, right? Or not $, I keep messing that up. DO asterisk, right? So I am looking for things that start with do. Okay, cool. When I break that up, it's going to be $D and DO, right? This is going to return on both of these dog. That's fine because it starts with D and then the next two letters are DO. That's good. Unfortunately, it also matches on didgeridoo because DO happens to live somewhere in that word. So if you're going to use k-grams to do wildcards, you either need to consider having long enough k-grams, so 2, 3, 4 length grams, which again increases the size of this secondary index, or you need to do a little bit of post filtering. So now it's small enough. This is not a big set of things that you have to do the post filtering on. You'd have to run through and say, hey, are these letters actually in order? I don't want to process this if it's not, right? Which is fine. That works. But these things will come up. They do matter, but this is a matter of testing. It's a matter of, you build it one way, you figure out, oh, I need a little bit extra to process this out. So using k-grams for wildcards is great. It's less storage than a permuterm index because you don't have to do every single permutation of a word. You just get to focus on what are the meaningful letter chunks. It doesn't require trees, and we're enabling partial matching using strictly the tables, the hash table solution. And that's because each k-gram itself is a whole term, right? It is a set of letters, and it's not something that we're only going to partially process. We're going to use that whole term to index into our hash table, which is critical. So makes them compatible. Okay, so great. We've found a way to get some wildcard functionality implemented in a strictly hash table way. That's fun. So in general, wildcards, the way you implement wildcard functionality will depend a bit on your structure. The best way to do them is not to rely directly on your structure and instead build some kind of secondary index to let you search for sets of terms, and then we'll turn around and use the sets of terms found from the wildcard to find sets of documents. If we do trees, we can exploit the natural properties of trees, still doing this secondary index using permuterms, right? That's a useful, easy way to walk through a tree to help you find the particular terms that you need for your search. But if we're going to stick with hash tables, we get a lot of mileage out of k-gram term indexes, and we will reuse them quite often for other things down the line. So this is a good thing to do. At the end of the day, do we really need wildcards? They add a lot of functionality for users who know about them, right? It can be quite useful to like specify just part of a term so that you can make sure that you get what you're looking for. Or even a better way to think of this is that users might learn a lot by using wildcards, right? They might figure out, oh, what's the thing I'm looking for? Let me do a wildcard search to figure out like what's out there among these terms that I sort of half know. And then they'll find the terms they want and they can go back and do the search again. So doing this gives useful features to your user, but it does cost storage and processing time. So as always, we can just do this selectively. If we'll go ahead and build the index when we build, we'll build the secondary index when we build the primary index, right? But we only need to bother processing a wildcard if the user actually uses them, right? We're not you don't go through all these tedious steps every time a user is gonna search something unless they actually need it. So, it's up to you if you want to allow this in a system. And I say you, I just mean anybody, right? They can employ wildcards in some of their systems and they cannot in others, right? I encourage you to try them out. Some search systems use them extensively and some don't implement them at all. But for our purposes, it's actually quite nice to go ahead and implement wildcards because kgram term indexes can help for other stuff. Things like spelling correction, which we'll talk about next time. So that's tolerant input, our introduction to it, and a full kind of rundown of wildcards in these search systems. We want to use, the idea being we want to give users a little bit of room to screw up, a little bit of room to not know everything about their search term, right? Because even with equivalence classes, we still assume the user knows what they're looking for. Whereas tolerant input says the user mostly knows what they're looking for, but we want to help them get there. So they can either intentionally underspecify a term, or we can say, hey, I'm going to try to help you correct that error because I didn't find anything when you did that. So wildcards help us with the underspecificity, but next time we'll talk about how to correct errors using some of these same ideas. So, final thought today. As you use the various search tools in your life, make note of the ways that they help out and are more tolerant of the raw input you give them. All right. Thanks and take care.